Paco. Yeah, so I'll be talking about what I'll call practical machine learning pipelines using Mllib. And for those who aren't familiar with the history of Spark Mllib, it started in UC Berkeley Amp Lab as a project there. It shipped with Spark 0.8. And since then, it's grown enormously. By now, at 1.3, contributions from 50-plus orgs, way over 100 individuals, and a pretty good coverage of algorithms from classic classification and regression ones to many more. And all of these are implemented on top of Spark using distributed data and have been run on some pretty large jobs. So I'd say Mllib's mission, broadly speaking, is to make practical machine learning easy and scalable with sort of two parts to that. One is you need to be capable of learning from large-scale data sets. And I think we've done a good job. That previous list of algorithms you saw, they've been tested on big data sets. They're constantly improving, and more algorithms are being added. The other part is making it easy to build machine learning applications. And there definitely have been big jobs, production included, on Mllib. But I think we can go a lot further, and we're making efforts to do so now. So the question is, how should we move beyond this list of algorithms and really help make it easier for users to create ML workflows? So there will be three parts. First, I'll introduce what I mean by an ML workflow with a simple running example. Then I'll talk about the Pipelines API, which is sort of our current solution to this, and then the roadmap ahead. So for ML workflows, I'll use a very simple text classification example. You may even be familiar with this 20 newsgroups classic data set. And what we'll be doing with it is, given this text document, which is a newsgroup post, we want to predict its topic. And there are 20 newsgroups, but I've lumped them together for simplicity into 1 about science and 0 not about science. So on the left, we have what I'll call features. And here it's text, but we'll also be working with vectors. You could have images and so on. On the right, I'll call these labels, what we want to predict. And that could also instead be other things. Click-through rate, inches of rainfall, a lot of things. But it's not important, really, what this data set or this task is. What's important is looking at the components of a workflow as we try to solve this task. Very broadly speaking, there are sort of two components to an ML workflow: training and testing, or production. In training, you're given labeled data for this problem, which will be an RDD of features, the text on the left, and labels on the right. And you have this information for each row or instance in your data set. Then you learn a model, which you can then use in testing or production, where you're given new unlabeled data, which in this case just has the text features. And you'll use that model to make predictions. This first one has the word Apollo and astronaut in it, so it probably is about science, and so on. Now, each of these two parts of our workflow are going to have several components, which will really resemble each other a lot. So let's look at training first. Well, we'll load data, which in this case will be labels and plain text. Extract features. And what this will be doing is taking that plain text and converting it into an ML-friendly format, like feature vectors. We'll train a model, and then that model will be able to take feature vectors and compute predictions about what we think the labels are. And notice I'm keeping around the labels this whole time. And that's so, of course, at the end, we can say we have the ground truth labels, the predicted labels, and we can compare them to evaluate how well we did. So it brings up the first pain point, which is if you look at a typical Spark workflow in Mllib, you often create many RDDs traditionally. For example, you might extract the labels as an RDD of doubles, might have features, RDD of vectors, predictions, and so on. And if you look at Mllib examples, you often see things like explicitly unzipping and zipping RDDs. Here, zipping the true labels and the predicted labels together so that we can compare each one. The next pain point is that while it is easy to write out an ML workflow, it's often easiest to write it as a script. The problem with that, of course, it's not modular, and it's difficult to reuse later on. This is a real problem when you move from training into production or testing, where you load new data but need to go through an almost identical workflow. And here it looks really simple, but in reality, you may have many steps of extracting features, maybe training multiple models, and so on. The final pain point I'll mention is each of these components can have parameters that you may want to tweak. When you extract features, you may need to know the number of features in that feature vector to do. Your model may have regularization or a number of iterations to run. And this is a key part of ML, tweaking those parameters based on your data in order to improve your final results. But what this involves is training many models for different splits of the data, for different sets of parameters, averaging results together, choosing the best set of parameters, and so on. And this is very doable. It happens in pretty much any code base you might be using. But there's a lot of sort of rote work involved in this. So these are 3 pain points: handling RDDs, writing scripts, and tuning parameters. And of course, our solution to this is going to be the Pipelines API. This was introduced in Spark 1.2 and has continued to be developed. It's still experimental, but it has a lot of nice features, and there's a great time to give feedback on it. So moving to pipelines. There are 3 sort of key concepts to pipelines which I want to mention. The first is the DataFrame, which is going to be sort of the de facto ML dataset. Next are several abstractions. And finally, I'll talk about a standardized parameter API for tuning. So hopefully you caught Michael's talk earlier on SQL and data frames. If not, I'll mention it quickly here, but won't be able to go into details. But basically, data frames provide a lot of the stuff we need for ML. A data frame is an RDD, essentially, which you're used to. But it also includes a schema, which is essentially a set of named columns with types. You know, in our workflow, we had labels of type double, text, type string, and so on. And by the way, I'm calling these columns because, you know, in a natural representation of a data set as a table, you may have 1 row for each instance or training example, and every column is a different aspect of that example. The other thing which this provides is a domain-specific language. Here, if we have a data set, I can say filter it by selecting every row for which the label equals 1. In that case, we're selecting the scientific articles for our problem. You can also do simple operations like scale every value in the label column by 0.5. So if you're coming from, say, R or Python pandas, this is a very familiar API, very powerful, expressive. And that's the idea, keeping it familiar. The big difference here, of course, is the RDD. This is working with big data, doing these simple operations, and having this powerful DSL, but operating on distributed data efficiently. There are a bunch of other aspects I can't really get into. You know, APIs in different languages, integration with Spark SQL, which has nice things like data import and export from different data sources, other optimizations I will mention a little later. But basically, this lets us handle this pain point of creating and handling many RDDs and data types. The next big concept I'll mention is abstractions. So here's our training workflow. We talked about loading data as a data frame. But for each of these 3 components, we've defined new abstractions. For abstracting features, we have the idea of a transformer. It takes 1 data frame and creates a new data frame. For feature extraction for our data set, what that looks like is we start with our loaded data with labels and text columns. And it's going to take that text column and create a features column and return all 3 columns as a new data frame. Now, this default behavior is to append new columns. But that's actually done efficiently, where if, say, at one point you need to inspect the features, you don't actually necessarily have to materialize the labels or text in memory. And this is done under the hood. But what this does allow, this append only, or this, sorry, I should say, it's not necessary to only append, but by default, it appends. And what's nice about this is that later on, you can go back and inspect intermediate results. The next part of our pipeline is training the model. And for that, we have the abstraction of an estimator, which takes a data frame and returns a model. So for us, you take your labels, you take your features, and you train a model to predict labels from features. And in our case, we'll be using logistic regression. The final part is evaluation. For that, as you suspect, we have an evaluator, which will take our final data frame and return some value. And this will be a metric, say comparing labels and prediction columns, and saying our scalar metric accuracy is telling us how well we're done, or how well we're doing, or area under the curve, or mean squared error, things like that. So this is our training workflow and the three main abstractions for it. I mentioned at one point that the estimator produces a model, and that we'll use in our testing workflow. But if we think about what the model abstraction actually does, it's a type of transformer. It's going to take the features vector for every row in our data set and create a new column with a corresponding prediction. So a model is really just a special type of transformer produced by an estimator. So I've talked about the different components of the pipeline and the corresponding abstractions. But what I haven't mentioned yet is the overarching abstraction of a pipeline. So to explain that, recall this is a slide I showed before about the estimator abstraction, where we're training a model, taking a data frame, returning a model. Now, what if I take this highlighted box and expand it to include extracting features? Well, this itself is taking a data frame and, at the end, returning a model. And so a pipeline concept is really just a type of estimator. Our full workflow is starting with a data frame of labels and text. And at the end, we want a pipeline model which can produce predictions about each of the rows of our data set. So as you probably guessed, in testing, very analogously, if we put a big box around our full workflow, that's a pipeline model. It's a transformer, and it can take the initial data frame and then produce one with the predictions and other intermediate results. So just to give you a way to step back and summarize, here on the left is training, right testing, with a bit of color coding. Black indicates the data frame we load initially. And blue is for transformers. On the left, for extracting features. Red is for estimators. And notice that after we've trained, on the right-hand side, we only have blue, the transformers, because all of the estimators have been fit, produced models, and now it's simply taking new data and making predictions about it, rather than fitting new models. And at the bottom, there are evaluators. So I'm going to take this image on the left and expand it just a little bit in order to show what I'll do in a little demo. The only change is that the feature extraction part has been made a bit more practical with 2 steps. And to explain what each of these do, I'll speak through how the data schema is changing as data flows through this pipeline. We start with labels and text, as always. What the tokenizer will do is take that text, which is the full article, and break it into a sequence of words. Hashing TF is a special featurizer which takes that sequence of words and hashes it into a fixed length feature vector. Numerical, easy for logistic regression to understand. And our final step, the training, is going to produce a model which can create predictions. So you can see how the set of data available to inspect grows as data flows through this pipeline. So let me flip to this demo quickly. Good. I think I need an extra here. OK. Sorry, it looks like I have to minimize that. So what I'll be doing is showing this workflow. This will be in Databricks Cloud, so there will be some things not available in the Spark shell, like visualizations. But the basic workflow is going to remain the same. So we're going to start, after some imports, by loading the data frame from Parquet. And if you're not familiar with Parquet, it's essentially just a nice columnar storage format, which allows compression and especially nice, I think, for ML data sets. So you can see I did a count on the documents loaded from this training data set, and there are 11,000 or so. And looking up, it's currently a very simple schema with the article ID, the topic, the text, and so on. And so what we can do is say something like, let's look at the various topics in this data set. And so what I'm doing here is basically showing off the nice data frame syntax, where you can do things like grouping by, aggregation, and so on. And then say C for each type of topic, how many of the articles actually correspond to that topic. So of course, as I said, we're going to put these into just two labels. 1 about science, and 0 not about science. Several of the original topics correspond to being about science, so we're grouping those together. So here I'm creating a label column, and if we inspect the training data set, we can see now that this data frame includes a column called labels of type double. We could say check the label distribution and see how many articles are actually about science versus not. We can see about 2,300 are about science. The others are not. So that's sort of our data loading part. And now that we've set that up, we can get to the interesting part of the ML pipeline. It'll have 3 stages: a tokenizer, the hashing TF, and logistic regression. Now, the way that we're going to define these stages is quite straightforward. We declare each stage, and we set its parameters. You can see here, hopefully, let me zoom in to make sure, that the tokenizer has an input column text, output column words. Hashing TF, set the number of features, set its input column to match the output column of the tokenizer, and so on. We do this for each of the elements in our pipeline. And finally, we can string all of these together with a pipeline which just is given those 3 stages in sequence. So now that we've created that, well, we have to actually do the data processing and learn a model. And for that, we can simply call pipeline.fit, giving it the training data set. And what that's doing is internally passing the data frame through that workflow and finally producing this pipeline model, which is a wrapper around both the feature extraction and the final logistic regression model. So we want to evaluate the results. For that, we could say make our predictions by taking the pipeline model, which is a transformer, transforming the training data set, which will create a new column of predictions. And then we can display it. And what this will show is basically just a subsample of the data and the corresponding columns: topic, prediction, text, features, and so on. So here, for example, there's an article about religion, and prediction is 0, as it should be. But going on to that evaluator concept, we can use what's called binary classification evaluator using the metric area under the ROC curve. If you're not familiar with that, basically close to 1 is perfect. Close to 0 is terrible. And what we're doing is declaring that evaluator and a little helper function, which we can then run on our pipeline model with the training data and see it's 0.999. We're doing almost perfectly. Great, right? Of course not for this demo. The model is overfitted. And the way to see that is to do the same thing, but run it on a new data set, which we haven't looked at yet, of test examples. And here, the ROC is 0.89. Not great. So how can we fix this? Well, for that, I'm going to return to here and explain the abstractions for parameters. So you saw this. This handles the issue of writing as a script pretty well, where you noticed when we loaded that test data set, I simply ran the pipeline model on the test data set. But what we haven't done yet is handle parameter tuning. So I'll mention quickly, we've put a lot of work into making the parameter API very nice. Parameters are typed, they're defaults, built-in documentation, autocomplete if you're in a development environment. For example, if you hit hashingtf.numFeatures, you get some info about it. It's an integer parameter, means the number of features, has a default value. You can set parameters in a reasonable way, and if you give it the wrong type or value, then it complains, and so on. But really what this is for parameter tuning. The standardized API lets us do the following. If we're given an estimator, say logistic regression, a grid of parameters to search over, and an evaluator to say how well a model trained on a particular set of parameters is doing, we can find the best set of parameters. So here, logistic regression has a parameter for regularization. We might want to try out a few values. HashingTF has a parameter for the number of features to produce. Try a few values. But of course, this can quickly get complicated. What the pipeline abstraction does is let us wrap this whole thing in an abstraction for an estimator, which is our pipeline. And now we can pass this pipeline to this class cross-validator, which can basically handle this tuning automatically for us. So to do that, I'm going to return to the little demo and look at parameter tuning. So I'm working with the same data set, same set of models, same workflow. But the goal here is to use k-fold cross-validation to tune parameters and not have to actually implement it ourselves. So first, I'm setting up a parameter grid. It's basically number of features by the regularization amount. And what this little helper method will do is build out this grid of 2 by 3 parameters. It's a toy example. Afterwards, to do the cross-validation, we have to specify those 3 components. Set the estimator, which is our pipeline, the evaluator, that binary classification evaluator, and the parameter grid we just gave it. And then we can fit this cross-validator. And I also specified the number of folds. That's for the k-folds, the k and k-fold cross-validation. If you try this out in practice, of course, use more than 2 folds in general. Often common to use 3 to 10, but really depends on your workload. So what this is doing while it trains is looking at each of these elements in our parameter grid and training on this number of features, this regularization, and testing each of these in sequence. As far as the 2 folds, it's training on one, testing on the other, and then vice versa. And at the end, what this will do is produce a cross-validation model. It's a model, yes, which contains basically the best workflow we found so far with the best parameters. And so we can inspect that. Here, I'm looking at that cross-validation model, choosing the best model from it. And the parameters that used were 10,000 features and 0.2 regularization. So the ROC for this test data now is 0.93. So it's significantly better than the 0.89 we had before. Good. So returning here, we had this pain point of having to tune parameters by hand. And we're trying to make efforts to remove that. So just to recap, we have these 3 main concepts for DataFrame, abstractions, and the parameter API. There are a lot of other parts to this pipelines API I won't have time to mention. The different languages, schema validation, which is basically checking for a valid pipeline before you run it, and so on. There are a lot of inspirations for this work. One is from scikit-learn, which has a pipelines API. But the nice things we really add are the Spark DataFrame for working efficiently with distributed data and a somewhat improved parameter API. MLBase is a Berkeley AmpLab project, which Mllib grew out of, and which continues to contribute. Basically, this pipelines work has been an ongoing collaboration with them. And finally, bringing us to the roadmap, I'll mention Spark.mllib is the primary ML package, and it has a somewhat lower level API than I've been talking about. Spark.ml is this higher level pipelines API for the algorithms in Mllib. So it's currently experimental, but growing rapidly. And now's a great time for feedback. In the near future, there will be more niceties added, like feature attributes, transformers, more algorithms. Looking farther ahead, there are many ideas from the AMP lab still coming, such as auto-tuning models, and also SparkR integration. So with this, I'll leave an outline up here of the talk, as well as a couple links which have more information describing the Pipelines API. And with that, thank you very much for listening.
Is it possible to export the best model so that it can be used by another session or another environment even?
Right. So that is, you're right, that is an important part of the workflow, but I didn't cover it here. In 1.3, we added model import and export for a lot of the models, although it is not there for all of them. But I think we hit a lot of the key ones, linear methods, ALS, decision trees and ensembles, and so on.
You mentioned that it's an experimental mode. What is holding back to make it production, and when it's, I think it will be production ready?
So I think the key thing is that the point of this is to be extensible. Users should be able to bring in their own data types, bring in their own transformers, their own estimators, and so on. And for that, we basically need to make sure we have proof from the community that people are implementing it and that it can be plugged in. I think once that is clear, and once it is possible essentially to be able to call any of the Mllib models from that experimental package, then we could declare it as it's stable. We know it works with this wide array of algorithms.
Take other questions.
OK. Yeah.
Thank you very much.
Thank you.